Starting the recording. Okay, so thank you very much for joining me this morning. So we're going to be reviewing the TExES Science 4 through 8. And so the content that will be in today's session is going to be good for anybody that is taking core subjects 4 through 8, because the science content will be exactly the same as if you're just getting certified in Science 4 through 8. And then if you are getting certified, if you're seeking certification in EC6, there is also going to be some of that overlapping content. So again, remember with the TEKS, right? The TEKS are, we kind of have that foundation, right? And we just kind of build on that information. So, you know, when we do a review for the Science 7 through 12, some of that content is also going to be repeated in that session. So everything that I'm getting for today is going to be coming from your preparation manual. So remember, in order to get there, you would be going to this NESync website. So on this website, you'll be able to find all of your exams. So I'll just click on the TExES, and then I'm going to be referring to the core subjects 4 through 8, just because the Science 4 through 8, it has like a manual, but it's the same exact competencies that you have to know, okay? So if you're here and your certification area is EC6, then I would suggest you open up the core subjects EC6. And if you have not tested yet, well, it doesn't really matter because the science competencies will be the same. So it doesn't matter which one of these you pick for science, the competencies will be exactly the same. But that way, as we're going through the information, you can see, you know, maybe there's a descriptor in there that we, you know, maybe didn't cover very well, or there's something in there that you feel you need to go back and review a little bit more or do some more research on. You can just kind of, you know, jot those ideas down. Okay, so when you open up your the exam, you'll scroll down to where it says preparation materials. And then in the preparation materials, you will click on the overview and exam framework. Okay, so in the overview and exam framework, it's going to give you all of your competencies. It's going to give you the descriptors. And then of course, this is just really just the overview of the exam. So if you're taking the core subjects 4 through 8, you'll only have 50 minutes to do 42 questions, okay? If you're doing the Science 4 through 8, there's a lot more questions, and you'll have the 5 hours to do it. So that's just kind of how that's a little bit different. So I'm going to scroll down just to get to the bottom here so you can see what the competencies look like. Okay, so here in the subject exam, it's going to tell you what the competency is. And so that's how I organize the review. So we're gonna go through competencies 1 through 10 today. And then the next review session we have, hopefully I'll be able to get through 11 through 24. That's a lot. So we might have to have a third one because there's a lot of competencies. But when you read your competency, it's going to kind of give you an overview of what you should know as a teacher. And this is what you're going to be tested on. So you know how we talk about TEKS in class, right? And so your TEKS are what you have to teach the students. And the TEKS are what the STAR test is based on. So if you're teaching to the TEKS, then your students should be successful on the exam. So same thing goes for your exam that you're taking. You have your standards. So you have your competencies and then you have your descriptors. So just like in TEKS resource system, how you can go into TEKS resource system and you can see the specificity, right? You can see all of those specific things that you have to go over. That's kind of similar to what these descriptors are. So obviously they're not as in detail, but it does give you a good idea of what you should be looking up and what you should be researching, okay? So for some of you that have already tested, if you've already tested and you have not been successful on the Science 4 through 8 or Science, you know, EC6 or whatever it may be, you can look at your report and it'll tell you which competency you didn't do well in. So you can go to that specific competency, look up these descriptors, and then that's the information that you would have to really focus on to understand, okay? So there are some things in here that I'm not gonna like go into like too much detail because I think it's kind of pretty common sense, I guess, you know, so, but other things I will try to make sure that I go over. Okay. So again, you'll find your competencies, you'll kind of read through them, and then you'll just make a note of anything that you do have to review or, understand a little bit better. And then if you attend all of the 4 through 8 sessions, so those of you that are doing core subjects 4 through 8 or science 4 through 8, if you attend all of the review sessions, then we'll go ahead and approve you to come in and take the practice test at the ESC. So with that practice test, if you score an 85% or higher, then we'll go ahead and approve you to take the TExES. Okay, so I know for some of you, you haven't finished with 240 tutoring, or maybe you just haven't had the time, or maybe you haven't had the money to finish paying for the subscription. So this is an alternate way of doing that. So you have to be present in the review, and then you would still have to come in and schedule a time to take the practice test with us. We're only in the office in the mornings. And I think right now we have somebody in the office Monday through Thursday. So that's when you would be able to schedule a review. If you're doing core subjects, then you would have to attend all of the core subjects reviews, right? So there's science, math, social studies, and ELAR. And then all of those they're probably like two to three 3-hour sessions. Okay, just because again, it is a lot of material. You have a question, Ivan?
Just real quick. This says you have to pass with an 85 or higher to get approved for the TExES exam. What is the passing score for the TExES?
So you have to score a 240, which works out to, what is that? I know it's less than a 70.
240 out of what?
Wait, maybe it is like a 70. 240 out of 300.
Yeah, I think that is.
A 70? Oops. It's an 80. Yeah. So so it's actually an 80 on the exam. Okay, good question though. All right, so again, here's the link. If you weren't able to get that, you can click on the link. This is going to take you to the Science 4 through 8, but if you already went to just the NESYNC website, again, you're going to find your exam, whatever exam it is that you're taking, and you'll just be kind of looking at the stuff that we have covered. So if you are here and you're doing EC6, the competency numbers don't quite match up, so you'll have to kind of go through there and see what we covered. Okay, and then again, for this link, if you already have it open, just have it open in another window, because we're going to refer back to it after we go over each competency. You'll be able to go back and look at what we did hit and make a note of anything we didn't hit, and those are things you'll have to kind of look up on your own. All right, so another thing that I did for this review is, because some of you in here are EC6, so I did put a little EC6 down here at the bottom for any information that pertains specifically to EC6. There may be a couple of things that go a little bit more in detail, but for the most part, I tried to keep the EC6 stuff like on its own, and then I just added onto it like on a different slide, okay, just to kind of help you out. So to get started, competency 1 is just looking at safety, right? So really making sure that you are having safe learning activities for your students. So in the elementary classroom, right, there's really not a lot of, dangerous stuff you're working with until you get to probably like 5th or 6th grade. And then once you get into, in the middle school, you may be able to use, items that are made out of glass, your hot plates, your beakers and all that. So basically just making sure you have a safe environment for your students, make sure that you wear proper protective equipment. So students should be using, aprons and goggles, at least goggles, because I know sometimes the campuses don't have the aprons, but they need to be using those, because even if you're working with something as simple as baking soda and vinegar, right, that can still get into kids' eyes. And, we just want to make sure that we teach them that early on, so that when they get into the high school, it's just a common practice. Just making sure you keep the areas clean. Not everything can go in the trash, especially when you're working with specimens or chemicals. And then make sure that you do handle organisms, whether they're living or dead, with respect and care, and really just teaching our students about that. And then you should always review safety procedures. So if you are teaching a science class, you should always start with lab safety. That's one of your first lessons in science, in the science classroom. And then typically campuses will have, or teachers, shall I say, will have teachers sign a lab safety contract, right? They'll have to go over all that and get parents to sign it as well, just so that everyone is familiar with the expectations. And again, most chemicals in the elementary classroom are typically just household products, but you may have some in the middle school where you might have some actual like chemicals, but for the most part, they'll stick to household products to use. So competency 2 is going to deal with the correct use of tools, materials, equipment, and technologies. So if you don't know the names of like science tools, I would definitely, look those up, beakers, flasks, graduated cylinders, balances, right? If you don't know what those tools are or what they're used to measure, you want to make sure that you look them up. So in the elementary classroom, right, for the little ones underneath 4th grade, when they measure things, it's very, it's like with cups, right? It's not like they're not actually using actual measurements, but once we get into the 4th grade, students are going to need to be understanding how to measure things. So actually using a ruler and reading it right, measuring with a graduated cylinder, your volume and liquids, and using a balance, whether it be a triple beam balance or like a digital scale, but students should understand how to use the numbers, right? And that the numbers, we have to use them exactly as we, they can't just, if it's like the balance says, 4.5, the kids can't just say, oh, it's 4, right? Like and we also have to teach them that all the numbers have units. Okay, so if you don't know your units, that's another thing you have to understand. So I put a real basic metric conversion chart here. Science, everything in the science classroom is done using the metric system. And the metric system is super easy to use, way better than what we use here in the United States, because there's all these, calculations you have to do. But with the metric system, it's really just about moving the decimal point. That's all you really have to do to get that going. Okay. All right. So with the metric system, these are like your basic conversions that you'll have to use in the classroom. And so it's a kilo, hecto, deca, then your base unit. So that one doesn't have like a prefix on it. Then there's deci, centi, and milli. And the way that you can remember this, and the way I would teach my students, was by using, this, oh my gosh, I can't think of the word. Well, God, I can't think of the word. Anyways, so I would tell my students, King Henry died by drinking chocolate milk. And I still, to this day, when I'm doing conversions in my head, that's what I say in my head. And that helps me to determine how many places I'm moving my decimal to the right or to the left. So for example, if I have like 1 kilogram, right? And I want to know how many centigrams that is, then I would say if I'm going from kilo to centi, so I would count how many spaces I'm moving. So from kilo to centi, I'm moving 1, 2, 3, 4, 5 to the right. And so if I have 1 kilogram, I would move my decimal point, 5 places to the right and add zeros in there. And that would tell me how many centigrams I have. Okay, so it's really just a matter of moving those decimal points. So if I have, 1 meter and I want to know how many hectometers that is, then I would say, okay, I'm going from a meter to the hecto. I'm moving 2 places to the left, right? So that would say that I'm going to have the 1 meter. So I'd move my decimal 2 places to the left, and that would give me 0.01 hectometers. Okay, so that's just how you use this conversion here. But again, everything in the science classroom is going to be done using the metric system. Another thing that you'll have to go over with your students has to do with precision versus accuracy, as well as the types of error. So this graphic really explains what the difference is. And so we want to make sure that we teach our students to be precise with their measurements. So we want to make sure that they're always measuring the exact same way, even to a point where maybe you have the same student, right, in a group, in a lab, you have the same student that's doing the measuring, so that the measuring is being done the exact same way. And so when you're precise, that just means that your measurements are close to each other, but it doesn't necessarily mean that they're accurate. Okay. And a lot of times when we're speaking just in general, in talking in the real world, right, we may use precision and accuracy to mean the same thing, but in the science world, they're different. So precise just means that the measurements are done closely together, so they're like reproducible the same. Accuracy means that the measurement is correct to the true value. So you can have precision without accuracy, accuracy without precision, right? Or precision and accuracy together. And so this kind of explains what that looks like. So just, making sure that we teach our students what those terms mean. And then in terms of error, students need to understand that when we do measurements, there may be error due to a variety of reasons. It could be the equipment, it could be the person, right? It could be just the, the environment that we're in. So just understanding that when we look at something in a textbook and it tells us this is what the value is, and then we actually go and we may, do an experiment to calculate what it is, it may not be exactly the same, right? Just because there's always going to be that bit of error. Okay, so if you go to your competencies, so I'm going to open up mine here. Okay, so for safety, right, we just did competency 1. So it says that we have to understand, right, safety regulations and guidelines for science facilities. You got to know procedures for and sources of information regarding the appropriate handling, use, disposal, care, and maintenance of chemicals, materials, specimens, and equipment. So if there's something in there that you need to look up a little bit further, right, just make a note of that. And then there are procedures for the safe handling, ethical care, and treatment of organisms and specimens, right? So we just kind of went over all of that. So again, that's just how the review's kind of put together.
Lewis had a quick question if the slides would be sent to us.
Yes, so I'm gonna send out an email, probably not till Monday, but it'll have the link to the YouTube video and it will have the a self-paced Nearpod code. I did with this Nearpod though, I did use my account. So if you actually take some notes, if you should be able to click on the notes on there. You can take some notes and it should email it to you. It should email the whole presentation to you with the notes. Okay, so we've got a couple of practice questions here. All right, so moving on to competency 3. Well, before we move on to competency 3, based on questions that you did on the little, mini quiz, jot down some notes, right, of anything that you may need to do a little bit more research on or study a little bit more. So again, it may be units, it may be measurements, it may be equipment. Okay. So competency 3 is going to deal with scientific inquiry and the history and nature of science. So there are going to be different types of investigations that your students are going to participate in. So there's descriptive studies where there's not really like any sort of measurement. It's really just like looking at, they're observing something. There's going to be comparative data analysis. So they'll actually gather data and then they're going to be comparing it, maybe to other groups in the classroom or to something that the teacher's providing. So just, comparison. And then there may be instances where they're actually going to do experiments. So they're going to be doing something and they're going to be looking to see what they're going to get, right? So they may actually have to create a hypothesis and, really think, right, about the concepts and how those may have an effect on what they're going to get. So it's important, especially for the younger kids, that they see stuff, because a lot of times kids are going to come into you with these, because they have their own world, right? So they have the way that they think things are happening. But when you actually have them do an experiment and they see it happen, that's actually going to make it more valuable than you telling them, right? Because it's like, well, who, even though you're the teacher, right? It's like, who are you, right? This is what I know. This is what my parents say, right? So it's important that you actually have students do the science. Okay, so these are some important concepts that you do have to know. So if you don't know any of these, make a note of them. These are things that you are going to have to, again, do a little bit of research on. And these are things that everybody has to know from EC6 all the way to 4 through 8. So there is the cell theory, and cell theory is something that students will even talk about in high school. But basically that all living things are made up of cells, and that everything arises from cells. Okay, so even down to the smallest living organism like bacteria, right? Everything is made up of cells. Plate tectonics, so continents on the Earth today began as a single landmass long ago, right? So the plates are always moving, and due to that, that's why we have our mountains that are formed, and why we have, volcanoes, and why we have the different continents. So just understanding that idea. And then there are Newton's laws of motion. I just realized I didn't put Newton there, but Newton's laws of motion. So there are 3 laws of motion, and we'll talk a little bit about them today. But the first one is Newton's first law of motion. So that's the law of inertia. So an object at rest will remain at rest unless acted upon by an unbalanced force. Then there is Newton's second law of motion. So force is equal to mass times acceleration, or reworded, acceleration is produced when a mass is acted on by a force. And then Newton's third law of motion, for every action, there is an equal and opposite reaction. And then the last one, universal gravity. So just every object in the universe attracts every other object along the line of centers. And that goes for everything, no matter how small, no matter how big. But of course, that's, that will be related to when we talk about physics, but that's also going to be related to like your Earth and space science. Okay, that's your astronomy unit and all that. So students also need to understand that in science, there are ethics that have to be followed. And so when it comes to data that is reported by scientists, the data should be honest. All data should be reported, right? Not just, you don't just want to nitpick the things you want to create, like share. So the same thing goes with our students in the classroom when they're doing experiments. We want them to be doing that same thing. And then if we use people, right, to do some sort of investigation, no matter what it is, we have to get their consent, right? So it doesn't matter if it's in the real world or if the students are doing a science experiment, right? So maybe a lot of times students are going to have to do science projects. And if students are working with people, they actually do have to get their consent. So there are forms that have to be filled out for students to actually be able to do the experiment and use the data. There are legal constraints based on rules and regulations of government entities in different parts of the world, right, that may also limit the type of experiments that can be done, right, due to ethics and other reasons. And so students should know that in the real world, right, there are rules that we follow, but in the classroom, we're also basically sticking to those rules. Okay, so just in terms of ethics. So in terms of data, students should be taught how to do all of these things, okay? And so if you don't know, how to do any of these things, just make sure that you look up like how that works. So if you don't know the scientific method, definitely look up what the scientific method is, right? So kind of starting with a question and then a hypothesis, and there's a procedure to follow there. And then making sure that students understand that we don't just come up with answers, right, in science, but there has to be data to back it up. So you have to be able to provide evidence for whatever it is that you're saying. And so that's something also that students need help with, right? Because let's say we're going to have them make a hypothesis. They may just give you some random thing and you're like, but that has nothing to do with what we're doing, right? So really trying to help them to understand what that is. And a way to help them do that would be claim evidence reasoning. It's a type of writing that you can do in the science classroom. So having students come up with their claim or whatever they think is going to happen, they have to provide evidence for whatever their answer is, and then they have to explain why that evidence is going to support their explanation. Okay, so having students really do that scientific method process. They should also be able to explain where there may have been error, like in an investigation. And then be able to communicate and defend their results, right? And so claim evidence reasoning, again, is a really good way to help students to be able to do this. And same for you, if you're not quite sure how to get students to be able to do this in the classroom, then that's what I suggest you look up. So claim evidence reasoning. And then also letting students know where to find legitimate information, right? So they can't just go on the internet, Google, and just take whatever's on there, but they have to make sure that it's coming from a credible source. If they, see something about the coronavirus vaccine, right, making sure that it is a verifiable source and that there is like scientific data to back it up. Okay, So we've got a couple more questions here. Okay, so competency number 4 is going to look at science and the daily lives of students, right? So competency 4 and 5, I think, are pretty straightforward. So all I did was just kind of listed what these descriptors were. So understands that decisions about the use of science are based on factors such as ethical standards, economics, personal and societal needs. Applies scientific principles and the theory of probability to analyze the advantages of or disadvantages of or alternatives, right, to a given decision or course of action. And then apply scientific principles and processes to analyze factors that influence personal choices concerning fitness and health, including physiological and psychological effects and risks associated with the use of substances and substance abuse. So this one is something that will be discussed all the way in like from EC6 all the way to like 6th grade and on, you know, into like high school, but making sure that students are making those correct choices in terms of what they're eating, you know, and making sure that they understand you need to exercise, you know, not using drugs, you know, using tobacco, drinking alcohol, just kind of stuff like that. So just being safe with your body. I think of this as more like a health concept. So then with competency 4, they also need to understand the concepts, characteristics, and issues related to populations and human population growth. And then understand natural resources, right? So in the world, we have a lot of natural resources, and a lot of these things we will cover in other, like in specific concepts, but students just need to understand that a lot of the stuff that we cover is not just like, it's not something that's just in the science classroom only, but they need to understand that that's happening in like the real world around them. Okay, so that's really what this competency is referring to. Competency 5 has to do with understanding the unifying concepts and processes that are common to all sciences. So again, all I did here was I just listed them all. These are all the descriptors that are found inside of your manual. So again, here in the manual, right, I just took them and I listed them. Just because competency 4 and 5, it's really just looking at science in general, you know, and looking at science in the real world. So just having students understand that, you know, it's not just isolated to the classroom. Okay, and again, I just listed those there. Okay, so a couple more practice questions here. All right, so again, with competency 4 and 5, they're not going to be highly tested just because they're kind of looking at that bigger idea. So moving on to competency 6, this has to do with forces and motion. So these next couple competencies are related to physics. So the key forces that need to be understood for this are gravity, electricity, and magnetism. Okay, so if you don't know what those are, definitely make a note that those are things that you are going to have to look up. So with magnetism, you just have to understand that the force of attraction or repulsion between objects with different charges, right? Magnets, that's what we're going to think of. They're typically going to be metal, and they're going to have two opposite poles to them, right? So you'll have a positive, which is north, and the negative, which is south. And it does relate to the earth, right? Like we literally have a north pole and we have a south pole, and you have a compass, right? That can be guided by that. So when we think of Earth, it's actually a large magnet, right? Because we do have those poles, and that's how our compass is able to work. And gravity is actually that magnetic field. Okay, that's what's actually causing that magnetic field. So everything, on Earth is being held to the surface of it due to gravity, and that includes the atmosphere, right? So even the air, right, that's around us, it's being held to Earth because of its gravity. And so objects that are more dense are going to have stronger gravitational forces. So that's why our sun, right? Our sun is massive, it's huge, it's super dense. And that's why we have all the planets revolving around it, because they're being attracted to it, okay, due to that gravity. So then next we get into force and motion. So these are, the main terms that you do have to understand. These are specific, right, to EC6. But again, in 4 through 8, you'll kind of build on these concepts a little bit more. So if you don't know what the terms mean, write them down, and you need to know what they are. Vectors are going to be more important, shall I say, or more specific to the 4 through 8 exam. So vectors, you don't have to really understand what a vector is in EC6, but 4 through 8, you do have to understand what a vector is. Okay, so when we look at force in motion, a position is just where something is located, right? So if I have like this, this would be my starting position here. And so when we look at distance, that's just how far an object has traveled. But when we talk about distance, we can also look at displacement, right? So I may take this long, windy path, but when I look at my start to my finish, my displacement is only like I literally just measure a straight path from here to here. So I could, walk around the block. And so I would have traveled a distance, but if I get back to my house, my displacement is 0, right? I went somewhere, but I came back and I landed in the same place. So that's kind of the difference between those terms. And when we think of the difference between a scalar and a vector, right? So that's going to be more specific to those of you doing 4 through 8. A scalar is going to be a number where direction doesn't matter, right? So I traveled, I don't know, 3 meters, right? But vector would be where direction matters. So I traveled 3 meters north, right? Or I traveled 3 meters, down my street or something, right? So just some sort of direction is going to be involved with a vector. And so displacement is going to be measured using a vector, but distance is going to be measured using a scalar. Okay, so it's not, no direction is involved with distance. And I do have a video there, but I know we're not going to have time to see them all, so I'm going to skip through that one. But that will be there for you to watch if you're not sure what I'm talking about. So then in terms of motion and speed, speed is just the distance traveled over time, and it is a scalar because the direction doesn't matter. And so to calculate speed, this is our formula. So we would take the total distance divided by the time, and that's going to give us our average speed. And then velocity is going to be a speed with direction. So when I talk about speed and I talk about velocity, we, like in the real world, right, we use both terms interchangeably, but in the science world, the difference is just that velocity has a direction. So it's my speed with direction. In 4 through 8, you have to understand how to graph speed, what is it? Speed, velocity, sorry, speed, acceleration, and position, like displacement. So you have to understand how to graph all of those things. So you have to understand how to read those graphs as well, okay? But this would just kind of be an example, right? So looking at time, as my time is passing by, you can see what my velocity is. And again, velocity is just a change in speed. So it's not necessarily, when we think of like, oh, I'm speeding up, right? So that would be like my acceleration, but acceleration can also involve a change in direction. Hope I'm not confusing you. I think I'm going to confuse myself. I don't know if I have time for that one. Okay. Yeah, we'll watch this one.
We've come to the Porsche Experience Center test track to talk about speed and velocity. And if we're going to do so, we might as well make it interesting. The term speed and velocity interchangeably, but in physics, speed and velocity are two very different things. In this segment, we're going to find out how and why this difference matters. The cars speeding behind me are moving with a lot of speed, but what does that mean? Speed is the rate at which an object covers distance. The SI unit for speed is meters per second. It's a scalar quantity, meaning it only has a magnitude. For scalar quantities such as speed, the direction the object is moving in doesn't matter. If the car keeps moving just as fast as it was before, except this time it's going the opposite direction, its speed still remains the same. Just because the car is moving in the opposite direction doesn't mean the speed is negative. Speed will always be a positive value. We calculate the average speed of an object by using this equation. The average speed in meters per second is equal to the total distance traveled in meters divided by the total time taken in seconds. Let's work through an example. When a car makes a lap around the track, we can calculate its average speed using the distance it traveled and how much time it took. One lap around this track is 1,600 meters, and the time it takes this car is 55 seconds. So the average speed was 1,600 meters divided by 55 seconds, which is 29.1 meters per second. That's pretty fast. Okay, we've talked about speed as a scalar quantity. What about velocity? Velocity is a vector quantity. It means it not only has a magnitude, but it also has direction. The SI unit for velocity is also meters per second. So when a car speeds past again, its speed is 71 miles per hour, or 30 meters per second. But its velocity is 30 meters per second going right. Average velocity is an object's change in position, or displacement, over change in time. We can calculate it using this equation. An object's average velocity in meters per second is equal to its change in position, or its displacement, in meters divided by the change in time, in seconds. When solving this problem with velocity, it's important to establish a frame of reference. Let's go to the track for an example. Say that right is the positive direction and left is the negative direction. A car is stationary at our origin point, point A, facing right. It's going to speed towards point B and turn around to stop halfway back to point A at point C. Would the average speed and the average velocity of the car over this journey be the same? Well, there's only one way to find out. It took the car 7 seconds to complete its journey. The total distance it traveled was 24 meters. This means that the average speed was 24 meters divided by 7 seconds, which is 3.43 meters per second. However, the total distance traveled by the car is different from the total displacement. The car's displacement only takes into account the point-to-point difference in meters between the origin and the final destination. The displacement from point A to point C is 8 meters. This means that the average velocity over the journey is positive 8 meters divided by 7 seconds, which is positive 1.14 meters per second, or 1.14 meters per second to the right. So it's possible for the average speed and the average velocity to have two separate values, even for the same journey. To recap, speed is a scalar quantity, which means it has magnitude only. Velocity is a vector quantity, meaning it has both magnitude and direction. But how are we supposed to know which direction is positive and which direction is negative? Good news, it's our choice. We pick our own negative and positive directions. So when you're given a problem to solve, indicate which direction you've picked to be positive. Whatever answer you get should reflect that choice. We usually treat right and up as positive and left and down as negative. So when the car was going from point A to point B, it was traveling the positive direction because we've designated right as the positive direction. If the car went from A to B in 4 seconds, then its average velocity was 4 meters per second going in the positive direction. But when the car was going from point B to point C, it was facing the other way. If it did so in 3 seconds, then it had an average velocity of 2.67 meters per second in the negative direction. Now, let's talk about the difference between average velocity and instantaneous velocity. Average velocity, as we've been discussing, is the displacement divided by the change in time. We calculated the average velocity of the car going from point A to point C. But what about the journey itself? The average velocity tells us the overall velocity over the course of the entire journey. The instantaneous velocity is the velocity of an object at a specific point in time. Let's look at the car as it was starting to accelerate and freeze it right there. At the time 0.5 seconds, its instantaneous velocity is 3.27 meters per second to the right. As the car speeds up, its velocity increases. What if we sped up to right here at 1.5 seconds? Its instantaneous velocity is now 9.81 meters per second to the right. Remember, the instantaneous velocity is the velocity of an object at a specific moment in time. Another important term to know is constant velocity, which is what we call unchanging velocity. Okay, so we've learned what velocity is, whether it's average, instantaneous, or constant. But how do we represent it? If we have a position time graph, we can use it to learn about an object's velocity. In a position time graph, the time elapsed will be shown on the x-axis and its position shown on the y-axis. This graph shows a constant velocity, which on a position time graph looks like a straight line. By looking at the slope of the line in a position time graph, we can learn about an object's velocity. It makes sense that this object is moving at a constant velocity because the slope of the line is not changing. We're covering the same amount of distance in the same amount of time. We can calculate the constant velocity by finding the slope of this line. If the velocity wasn't constant, we can calculate the average velocity by drawing a line between 2 points in time and find out the slope of that line. If we want to know the instantaneous velocity, or our velocity at a given point in time, we can draw a tangent line from that point in time and find the slope of the tangent. We can also have graphs that look like this, with the line going up and down. This point indicates I'm moving in the positive direction away from my origin. This would be me moving at a constant velocity away from my origin in the positive direction. This point right here would indicate me turning around and moving at a constant velocity in the negative direction. It doesn't mean that I'm going any slower or faster. The negative slope just means that I'm moving back toward the origin in the negative direction. Remember, the slope of a line on a position time graph tells us the velocity of the object. For a more detailed analysis of position time graphs, see Unit 2, Segment D on graphing motion. We've talked about speed and how to calculate the average speed of a journey using distance covered and the time taken. We've talked about the difference between speed and velocity, and the differences between instantaneous velocity, constant velocity, and average velocity. We've also looked at how we can deduce magnitude and the direction of velocity, both average velocity and instantaneous velocity, by looking at the slope of a line on a position time graph. That's it for this segment of Physics in Motion. I've enjoyed myself. I hope you have too, and we'll see you next time. For more practice.
All right, so Physics in Motion is a website I recommend. I'm sorry, not a website, a channel I recommend that you take a look at on YouTube if you need more help with the physics videos. They do a really good job of explaining the math. You notice they talked about the math, they talked about the graphs, they talked about the concept, and then they showed it in like the real world. So that'll help you understand that a little bit better. So for EC6, you have to understand the main like concepts. But when they talked about like the positive velocity and the negative velocity and all the different graphs, that's going to be more specific to the 4 through 8. Okay, so those of you doing 4 through 8, you do have to understand what these graphs will look like, how to graph, how to measure, and how to describe what's happening in them for displacement, velocity, and acceleration. I know for me, I still sometimes get a little bit confused between the different graphs. Like I really have to think like, okay, you know, if I'm looking at the graph, like what is this actually saying? So if that's something you need to review, you know, definitely go ahead and do that. So on the next video, on the next page, there's a link where you can actually see the 3 graphs of displacement, velocity, and acceleration. And it allows you to move it so you can kind of see how they all affect each other. All right, so if you want to go ahead and click on the link, and it'll take you to this page and you'll see the 3 graphs. And on the 3 graphs, you'll be able to move, like where the point is, you can actually move it and you'll see how it affects all the other graphs. So I think this is a good way to get a better understanding of how all of these graphs are related. So all of these 3 graphs are talking about the same object doing the same motion. It's just showing you how they're going to look different, you know, in terms of all the graphs. Okay, so if I move this one, right, I don't see like any changes that happen, but I can move points on here. And it shows me how all of these graphs are going to be affected because of that. Okay, so that's just a good little example to help you visualize, right, like what it is that is happening. Okay, and again, on the self-paced Nearpod, you'll be able to access everything that I'm sharing with you here. All right, so next thing has to do with Newton's laws of motion. So again, we talked about them on what is it, competency 4 or 5. But with Newton's first law, that is the law of inertia. And so this one, a lot of times you'll have to explain it, they'll use like car crashes as an example. So, when if an object hits something, right, like in a car crash, for example, whatever's inside, right, you as the person, you're going to keep moving forward. And that's why people, for example, like fly out of windshields, if they don't have their seatbelts on, that they're going 60 miles per hour and they hit something, their body's going to keep going 60 miles per hour, out the windshield or whatever. This one has to do with an object in motion, staying in motion, but it's also going to have to do with an object at rest. So that could be, for example, if you've seen that magic trick where they have a table and they've got all these, dishes on top of it, plates and cups and all that, and they have a tablecloth and they just like yank the tablecloth out and all the stuff stays there, right? That's just the law of inertia showing you as well. So objects at rest are going to stay at rest unless a force acts on them, and an unbalanced force, right? So something that's actually going to move them. Okay, Newton's second law has to do with force, mass, and acceleration. And so if you don't know what a force is, it's just a push or pull in an object. Mass is going to be the amount of matter that's found in an object. And then acceleration is going to be the change of velocity of an object. So in the video, she didn't talk about acceleration, but I know that Physics in Motion website does have a video that discusses acceleration. So acceleration is also, it's really just looking at a change in velocity. So acceleration can happen if I speed up, if I slow down, or if I change direction. I could be going at a constant speed, but if I change direction, then I am technically accelerating. Okay, so if I'm on a merry-go-round, for example, right, once it starts up and I'm going around, my acceleration is always changing because I keep turning. I'm not going in one straight direction, even if I'm going at the same speed. So with Newton's second law, it's looking at the amount of mass and force that you have and how that's like affecting acceleration. So for example, right here, I have this huge elephant, right? And we have this little person here. And so they're applying a force, but they're not going to be able to do, cause much acceleration in the movement of the elephant due to their small size, right? In comparison to that. So I could, another example would be if I take a bowling ball and I try to throw a bowling ball, because of its mass being so huge, there's not going to be much acceleration, right? Because I can only produce so much force. But if I were to take like a golf ball and I were to try to throw that, the mass is so much smaller. And so my force, right, it's still the same force, but I'd be able to cause it to accelerate like much larger, a much bigger amount. So it just is looking at those differences. Okay, Newton's third law of motion has to do with, it's also referred to as like the action-reaction force. So for every action, there's an equal and opposite reaction. And so we have some examples here. When someone is swimming, right, they're actually pushing on the wall and the wall is actually pushing like back on them. So because of that, that's how you're able to move in one direction. When you're rowing a boat, right, you're actually pushing the water in one direction and the water is like pushing you forward. So with Newton's third law, it's really understanding that forces work in pairs. So there's always going to be two things. It's not just like in the balloon, it's not just the balloon, moving forward, but it's actually that there is air coming out of it and there is the movement of the balloon going the other direction. Okay, so it's looking at two opposing forces. Okay, and then there is a video there that talks about Newton's laws, but I'm gonna have to move on. Okay, so the next link, if you take a look at the next link, it actually has some really good physics like tutorials. So if you click on this one, it has some good like animations to help you understand them. So if there's anything that you're not quite clear with in terms of the graphs or in terms of like the calculations or, what the positive, what the negative means, on this site, you'll be able to see it. There is, so this one will be useful for the middle school and going into high school. So those of you that, if anybody's here for 7 through 12, this one will be super, super useful. The physics classroom has a bunch of tutorials and they were super helpful when I was doing AP physics, okay? But some of these things in terms of one-dimension kinematics will be helpful for 4 through 8. Okay, now in terms of physics, the next thing that you have to understand has to do with machines. So simple machines and complex machines. And so in the elementary, so EC6, you're looking at understanding what the different types of simple machines are. And basically all they are things that are going to make it easier to do work. And so with the simple machine, they're going to have few or no moving parts, right? So if I think of like my computer, that's definitely not a simple machine, right? But we're talking about like a hammer or a screw, right? The doorknob there is an example. So with these ones, it's just changing the amount of force or the direction of force in some cases. And so it just makes it easier to do the work. A complex machine is two or more simple machines working together. So for EC6, you have to understand like what the machines are. For 4 through 8, you've got to understand how force and work is affected. So looking at it a little bit like more in depth. Okay, and then so that one, you can play that one on your own, but this one should explain. There we go. So this one should explain how the forces are affected. So this one will be more specific to 4 through 8.
Lots of different forces help shape all the planets in our solar system, including the Earth. Find out more on Science Trek. The Earth is about 4.5 billion years old. It has an inner core of solid metal, surrounded by a layer of liquid metal. Next is the mantle, a multi-layered collection of hot, heavy rock. The mantle is about 1,800 miles thick. And on top is the rocky crust. That's the part of the Earth we see, the part we live on. Geologists believe the Earth was shaped by lots of different forces over periods of time. And by studying the layers of rock and dirt and exploring the contours of the land, you too can learn how those forces shape the Earth. The surface of the Earth is made up of bits of land known as plates. These plates are moving, sliding past one another, folding underneath, or butting up against each other. When the pressure between two plates builds up to more than the rocks around them can stand, the plates crack, and the energy is released in what we know as an earthquake.
You can see why an earthquake can cause a lot of damage. Put 2 wood blocks together and cover them with a layer of sand. Put a few buildings and animals on top, and then move one of the blocks. And that's what an earthquake looks like.
Earthquakes are most common where the plates meet. That's known as a fault line, and Idaho is number 6 on the list of states with the most earthquakes. A volcano is basically a hole in the Earth's crust where lava comes out. Lava is hot, molten rock.
Lava has viscosity. Some lava, like this toothpaste, comes out thick.
Other lava, like this ketchup, comes out like a liquid.
Eventually, the lava cools into rock.
Ancient volcanoes created the twisted landscape you see at Craters of the Moon National Monument. In some parts of Idaho, the mountains were formed when magma, or hot lava still underground, pushed upward but didn't break the surface. That's called a batholith. These mountains are part of the Idaho batholith. A little bit of water can completely change a landscape. Over time, moving water eats away at rock. So thousands of years later, what was a plain can become a valley. A flood can dramatically change the landscape. 15,000 years ago, the Bonneville flood scoured out the Snake River Plain, carving out the canyons at Twin Falls. And not all floods are caused by nature. When the Teton Dam broke in 1976, a wall of water almost wiped out many small towns, including much of Rexburg.
How fast the water can erode the land depends on how fast the water is flowing. A gentle flow doesn't have much energy, but a flood has lots of energy. So the amount of damage to the land depends upon how much energy or force is involved.
Glaciers are rivers of ice that carve their way through the land. They grow and push their way through, creating U-shaped valley with a flat bottom and high sides. Even water in the form of rain can reshape the earth. Too much rain all at once can cause landslides. And even gentle rain and snow over time can wear away the top part of the earth, showing the harder rock below. Freezing and thawing can also crack rocks open, making it easier for water to eat away at the surface. Erosion, especially over time, can sculpt the land. Water in all its different forms is one of the major forces that shape the earth. What forces carve the earth where you live? If you want to learn more, head to the Science Trek website. You'll find facts, links, games, material for educators and parents, and much more.
Okay, so go ahead and take a look at your manual just to view the descriptors that were related to this one. So this is the one of the physics components. But if you'll notice for this one, for 4 through 8, where are we? There we go, forces. So you have to understand the different forces, but then you also have to understand how they work it mentions a variety of situations, right? So not only thinking about, just like, I don't know, objects, but also looking at like Earth, and so that's why that video kind of mentioned how forces are going to be involved in that. So again, just go ahead and read through these descriptors for the forces of motion, that like physics component. And then again, just jot down some notes on anything that you may have to do a little bit more research on, or that you need to understand a little bit better. Okay, we good for me to move on? Thumbs up. All right. Okay, so let's try some more practice questions. So competency number 7 is going to deal with the physical properties of and changes in matter. So this one's focusing mostly on physical properties for the most part. So matter is going to be anything that has mass and takes up space. And again, this competency is dealing with chemistry, okay? So mass is going to be the measurement of the amount of matter in an object, and that's always going to be measured with grams. So we don't use pounds, okay? No pounds, no English system in science. And then volume is going to describe the amount of space that matter takes up. So again, with volume, we'll be measuring that with liters, right? We're not going to be using gallons or pints or anything like that. So liters is going to be our unit of measurement. And when we think of matter, right, matter is made up of atoms. Like all matter is going to be made up of atoms, and those atoms are going to be taking up a certain amount of space, and they have like attractive forces that hold them together. And that's why they have their shapes, and they, have their specific volumes and all of that. So it has to do with the particles that actually make them up. Okay, so there's a video there if you want to take a look at that later. So when it comes to physical properties are going to be a way to describe matter without changing the composition. And so a physical property, if I have an object, right? I don't know, I've got my mug here, right? So if I have my mug and I wanted to describe my mug, the way I would explain this to my students when I taught this in chemistry is I would tell them physical properties are going to be things that you can observe with your 5 senses, right? Or it's also going to be something that you can actually measure about it. So a physical property of my mug would be that it is red. I could measure its mass. It's going to have a certain mass to it. It's got kind of a little bit of a shine to it, like its luster. So that would be its luster. I could look at its volume, see what volume it holds, maybe like a 1.5 cups, right? Of liquid. I could see its like its strength, right? If it's going to be malleable or not, right? This isn't malleable. It's not going to bend or anything. Like if I try to, bend it, it's going to crack on me. And so physical properties are things I can observe with my five senses, or something that I can measure without changing the composition of the item. So if I wanted to measure the density of this, I could. If I wanted to measure the melting point of my cup, right? I could do that. That would totally destroy my cup, but I could, try to measure that, right? I could measure its solubility. I could see if this dissolves in water. This doesn't dissolve in water, right? But that's something that I could do to describe my mug here, okay? So that's just what physical properties are. Okay, and I think, let's see.
Have you ever wondered why ice turns into puddles of water on a sweltering day? Keep watching and you'll find out. On Earth, materials exist in one of three main states of matter: solid, liquid, or gas. Materials can change between these states. When a state change occurs, a substance's property will also change. Maybe not too surprising. However, if the state change is reversed, the substance will recover the properties it had to begin with. Neat. Matter can transition between the three states when heated or cooled. But why is heat key in all of this? When a material is heated, it absorbs heat energy. This additional energy can cause attractive forces between molecules to break. This leads to rearrangements of the particles because the attractive forces no longer hold them together as tightly. The same happens when a liquid is heated. The attractive forces between the molecules break, leading them to become more widely dispersed and a gas to form. These four words describe changes in state. Do you know which word refers to which change? Pause the video, fill in the gaps, and click play when you're ready. Did you get them right? Do you know the difference between evaporation and boiling? Both are when a substance transforms from a liquid to a gas. Think of a boiling pan of water. All of the water bubbles. This is because all of the particles have enough energy to become gaseous. But water standing in a pan that is not being heated by anything other than the environment can also turn into a gas. This is evaporation. Only the particles at the surface have enough energy to change from a liquid to a gas. Hence, evaporation is a slower process than boiling, even though it achieves the same state change. Both are types of vaporization. The opposite of these vaporization processes is condensation, the transition from a gas to a liquid. Think of a cold can of soda on a hot day, those water droplets on the outsides, or the dew on the grass in the morning, or the steamed up mirror after a hot bath, even the clouds in the sky, or a foggy windscreen in a car. These are all examples of condensation. Water vapor in the air has cooled down to form liquid droplets of water. Now let's think about the transitions between solids and liquids, so melting and freezing. Think of the Arctic sea ice. In the summer, when air temperatures are warmer, more heat energy is absorbed by the ice. This causes bonds to break between the ice's water molecules and the ice starts to melt. The solid ice becomes liquid water. But in the winter, the air temperatures are colder, and so seawater freezes, and the ice starts to form again. There is less heat energy within the ice, and so more bonds can form, holding it together as solid ice. So far, so good. But did you know that sometimes when solids are heated, they can turn straight into gases? This is called sublimation. This is only demonstrated by particular materials such as solid carbon dioxide, also known as dry ice. When subjected to a certain pressure, it will turn straight into gaseous carbon dioxide. Liquid carbon dioxide does exist, but it only occurs under very high pressures. Similarly, gases can turn straight into solids when cooled. This is called deposition. Let's check out how much you remember about the changes of state. Pause the video and fill in the blanks. Did you remember them all? Our final thing to discover is that when a material changes states, the mass stays the same. The density changes, so the mass per unit volume, but the mass does not change. Our glass of nice cold Coke weighs the same whether the ice is solid or when the ice has melted. So there we have the changes of state. Just remember that the mass stays the same whatever the state.
If you liked the video, give it a thumbs up and don't forget to subscribe.
Okay, so with phase changes, I think a lot of the terms when I would teach chemistry, a lot of like this stuff that we're going over right now, I would always have my students do foldables and I would have them do definitions with pictures. So there's a lot of different terms, right? And we're talking about different, like with the phase changes alone, right? Going from solid to liquid, liquid to gas, a gas to a solid. They all have these specific names to them. So if there's any terms that you don't understand, I think what would be super helpful is also to include some sort of a picture. Okay, that's just a good way to teach your students, but also to help yourselves when you're studying. So when it comes to particles that in our atoms and all that, the molecular structure, and we talk about molecular structure, we're talking about like the atoms, the compounds, that are forming them. We're talking about how they're actually arranged. So because of their arrangement, it's going to cause things to have certain physical properties. Okay, so just like right now in that video, they were talking about phase changes and they were using water as an example. So water's a really unique, it's got a very unique chemical structure to it because it kind of has slightly positive and slightly negative charges. And so that's why water, if you've ever, put a bottle of water or something in the freezer and it freezes on you, it explodes, right? If I put a bottle of water in there, it's going to actually expand. So water will expand when it freezes, whereas not everything is going to do that. Okay, but it has to do with the molecular structure within it. So when we think of metals, metals are going to have unique physical properties to them because of the electrons that are inside of them. So with metals, you're going to have these ions that are going to be close together, but you have these electrons on the outside. And because of the electrons, it kind of forms this, like, I guess it's like a sea of electrons, right? And so because of that, it has these properties of being very lustrous, right? So metals are going to be really shiny. They're going to be malleable. So you can hit them, right? You can hit them and you can flatten them. That's how they kind of like, they do metal work and stuff. You've seen them like make swords, right? So they'll be able to hit them and they heat them up and they can cause them to change their shape and they're not going to just shatter on you, right? I can't take my mug and try to like, hit it and try to make it form some sort of like flat structure. If I hit it, I'm just going to break it, right? It's brittle. But for metals, they're going to be malleable. So I can hit them and I can cause them to change their shape. And it all has to do with that sea of electrons. They're also ductile. So they can be like drawn into like wires. And then they're good conductors of heat and electricity. Okay, so that's something unique to metals and it has to do with their molecular structure. So when I'm looking at the actual atoms and the electrons inside of the atoms, that's what's causing that to happen. When we look at crystals, crystals are going to have unique physical properties, again, because of the structure of their molecules. So these are some examples that you have here. And so when you, in middle school, if you're teaching about, like minerals and stuff, right? This is kind of where you would talk about crystals, but crystals are going to have unique like geometric relationships inside of the structures. And so because of them, they're going to have certain properties of hardness, cleavage, optical properties, heat conductivity, and electrical conductivity. So like with a crystal, if I were to like hit a crystal, I'm not going to be able to, flatten it or anything, but it's going to break, and it's going to break a certain way because of the attractive forces within the molecules. So wherever the molecules are like weakly bonded to each other, that's where it's going to break. And so I'm going to end up with that same kind of like structure to it. So it doesn't just break and crumble into like, pieces, but it'll break along certain cleavage points. And so you'll be able to see those same types of structures even in that broken piece that you break off. And then polymers, they can be either synthetic or they can be natural, but they have really large molecular structures, okay? Meaning that they're made up of a lot of different types of atoms. And so because of that, they have these unique characteristics, such as having toughness, They've got high elasticity, viscoelasticity, and a tendency to form amorphous or semi-crystalline structures rather than crystals. So they won't actually form a crystal, just kind of be like a, you know, a glump. If you've ever melted like, you know, something in the microwave or in the heater, in the dishwasher, right, in the oven or something, you're just kind of like turns into like a blob, right? So that's what polymers are. And, you know, the most common polymer that we're going to see is going to be like plastic. Okay, so that's something that we see everywhere now. Now with elements, so when you're taking the science 4 through 8, you are going to be given a periodic table. So you do have to understand how the periodic table is arranged. But your elements are going to be everything that's on the periodic table. I just realized this one does not have my inner transition metals. Okay, so anyways, there should be another portion down here. I just noticed that picture is missing it. This one's just looking at the ionization energies. I must have totally chosen the wrong picture here. So with your periodic table, it's going to be made up of atoms, okay, and they're arranged on there in a specific way, and it has to do with the amount of protons that are found inside of them. This is a really bad picture, so don't use this picture as reference because this is only talking about ionization energies, which you would use in chemistry, like in high school. So the atoms are going to be made up of protons, neutrons, and electrons. And the periodic table is arranged according to the number of protons in each of your elements. And so 2 or more atoms that are covalently bonded together produce molecules, and 2 or more different elements that are ionically bonded together are going to produce compounds. So you do have to understand the difference between molecules and compounds and the different types of bonds that can be formed. And I think we have time. I think we're still doing good. So this is just a quick overview of the periodic table and how it's arranged.
The elements. Okay, we're done imagining for the episode. That was fun though. The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkali metals, so reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation, and they're always jonesing to hook up with a hottie from the other side of the table. So of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals, reactive metals, but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions, or anions with 1 negative charge, and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gas.
Okay, sorry, cut that just a little bit short. So the you do have to know the periodic table and the properties of the elements. So like in that, and again, that's going to be more for 4 through 8. Okay, so with the periodic table, each of your groups or your columns are going to have specific physical properties to them, and they're going to react certain ways because of where they're located. So you do have to know what those properties are and kind of how that periodic table is organized in general. So on the periodic table, right, if you'll notice, he mentioned that the metals are like the majority of like one section. You've got your metalloids kind of like they're usually on a periodic table. If I had chosen a right periodic table, you would have seen like a staircase. And then you'll have your non-metals that are going to be like on that far right. Okay. So with the periodic table, what I used to do with my students is I would actually have them color it and label it just so they could visually see, right, where you have the metals and non-metals. And when it comes to atoms bonding to each other, when we're talking about covalent bonding or sharing of electrons, which we'll talk about in a little bit, that's going to happen typically with your non-metals. So on the top, like right hand section, I guess you could say. And when we have ionic bonding or atoms that are going to be giving and taking electrons, that's going to happen between metals and non-metals. So opposite sides of the table. Okay, so then physical and chemical changes are something you also have to understand, and they're not to be confused with physical and chemical properties. Okay, so they're different. So properties are ways to describe matter, and changes are, literally that it's a change that the matter is going through. So a physical change is going to be a change in a substance that does not change the original composition. A physical change would be, for example, in that video that we saw where it was talking about the changes in phase, right? So if I'm going from a solid to a liquid or a liquid to a gas, that is a physical change, right? So if I have water and I freeze it, it's still just water, right? It's just solid water. If I have water and I boil it, it's still just water. It's just gas water. So that's a physical change. One misconception that sometimes students are given when they come into the high school is they think that a physical change can always go back. Like you can fix it, right? So if I have a paper and I cut the paper, students may be confused because they'll say, well, I can't put the paper back, right? So it's not a physical change, it's got to be chemical. Well, it's still just a paper, it's just a torn paper. Okay, it didn't change any of its properties. So then a chemical change is going to be when a substance reacts with something else and becomes a new substance. And so in a chemical change, there's going to be indicators for a chemical change, which are these bottom things down here. And that's how I would tell my students, that's kind of like the litmus test, right? So if something changes, I'm going to ask myself, was there a change in color, right? So if I take my paper and I cut my paper in half, so I've got like my yellow paper here, if I cut it in half, did the color change? No, right? Was there a gas produced? No. Does it smell different? Nope, doesn't smell any different, right? Was there any heat or light produced? No. So then I know that this is still just a physical change, okay? But if I were to take my paper and I were to light it on fire, I'm gonna have a change in color, right? It's gonna turn black. I'm gonna have a gas produced. You're gonna see smoke coming out. It's gonna smell different. And lighting it on fire is gonna produce heat. Okay, so that's kind of your main like litmus test to see if you have a physical or a chemical change happening. And then there is a video there to kind of go over that, so you can take a look at that later. So for phase changes in that video that we watched, it talked about going through those different phase changes, but just when it comes to graphing, just understanding that when I have two phases of matter existing, the temperature will remain the same. So if I have like ice cubes, right? At my ice cubes, I can take down to maybe a temperature lower than 0 degrees. But once my temperature gets to 0 degrees, that's where it's going to start to melt, right? 0 degrees Celsius. And so as long as I have ice and water existing, that temperature is going to stay the same. It's not going to be able to change temperature until all of my solid is gone, right? Once I don't have any more ice cubes, then the temperature will start to increase. And then as it starts boiling, that temperature is going to stay the same. So again, I would think about my students, and my students, if they had, we would talk about these phase changes and they would say, yeah, well, when I have water boiling, I turn the heat up higher so that I could get it even hotter. But it doesn't matter how much heat you add to it, it's still only going to be at 100 degrees Celsius because that's the boiling point of water. As long as I have water and gas there, it's going to stay 100 degrees Celsius. Once all the water is gone and I'm stuck with my gas, then that temperature can start to rise again. And this goes for any substance, right? It's going to have these temperatures that will stay the same as long as I have two phases. Okay, now in terms of real life, right, in the real world, we just need to understand that when we're talking about, and I think of just like earth science, of course, there's other situations, but in earth science, we're going to have physical properties that we can measure. And because of that, we'll be able to also see like physical changes. So like, for example, in the water cycle, you know, when we teach the water cycle, we can also let students know that it's because it's a physical change that's actually happening, right? So with the water cycle, you know, you've got your clouds and, you know, you have your precipitation and you've got your, you know, your water that's going to evaporate, right? This kind of cycle. And it's just a physical change that's causing that to happen. And then when we think of like the atmosphere, for example, the changes in atmosphere, you know, depending on how high or low you are in elevation, it really has to do with the molecules and how like closely they are to each other as to why you would have higher pressure or lower pressure, you know, hence why, you know, when people go hiking like super high in the mountains, right, they may actually have to take oxygen with them because there's just not enough up there for them to breathe. Okay, but it really has to do with just the particles and how close or how far apart they are to each other. Okay, so for competency 7, again, go back to your manual. And I'd like for you to go ahead and read through these descriptors and then make a note of anything that you may have to go back and understand a little bit better. Okay, so again, make sure that you are looking at your subject test. So if you're EC6, make sure you're looking at EC6 and just looking at that chemistry competency.
Miss Monique, or not Miss Monique, sorry, Miss Hinojosa, sorry. Is it all right if I take off at 11? Is that okay?
Yes.
Thank you. Sorry about that.
That's okay. Okay, and just give me a thumbs up when you are ready. All right. Okay, so then we have competency 8, and this is looking at chemical properties and changes in matter. So with this competency, we have to understand the atom and the periodic table a little bit more as well. So just to review the atom, it is the smallest unit of matter. It's made up of a nucleus, right? So you have your nucleus here in the middle, and the nucleus itself is composed of protons and neutrons. Okay, so, oops, I just realized I highlighted the wrong term here. So it should be neutrons, not neutral. But protons and neutrons are going to be found in the nucleus, and that is what's going to give an atom its mass. So this picture or this model may be deceiving in that it looks like the electrons are like the same size as protons and neutrons, but electrons are actually so small. And they move so fast that you can't even like see them, you know. They are able to kind of detect like the masses, and so the protons and the neutrons, but with the electrons, they're so small that you can't actually see them. So they're super small in comparison to protons and neutrons. And a lot of times in models, they're going to model them like this, where they have these like clear orbitals, but in real life, they're not like that. They're just moving so fast and moving around. And so they talk about them in terms of like energy levels. So you'll have electrons that have, I guess, lower energy. So they'll be lower energy levels. So they'll be closer to the nucleus, but they're not necessarily like in that specific, you know, a clear orbit, the way the planets orbit around the sun. Okay, so that's a misconception. But this is a good way to explain that the movement of the electrons and how many electrons an atom actually has. Okay, and so how much time do we have? 2 minutes, yes.
Atoms are the fundamental unit of matter. They're made up of 3 types of subatomic particles: protons, which are positively charged, electrons, which are negatively charged, and neutrons, which have no charge. Protons and neutrons are located in the nucleus at the center of the atom, while the electrons orbit the nucleus. Let's take a quick look at an atom of carbon. Notice how the 6 protons and 6 neutrons reside inside the nucleus, while the electrons are shown in orbits surrounding the nucleus. The number of protons identifies the element. All carbon has 6 protons and therefore 6 electrons. However, there may be minor variations in the number of neutrons in atoms of an element. These variations are called isotopes. It's a little difficult to show the exact location of an electron. This is because electrons have almost no mass and orbit the nucleus of the atom at incredible speeds. Therefore, their precise location at any given moment can't be determined. For this reason, electrons are often shown as a negatively charged cloud around the nucleus. However, other diagrams show the electrons as existing in rings or orbitals. Orbitals are often used to illustrate the number of electrons at different energy states surrounding the nucleus. This is important because only the electrons at the highest energy states, or outermost orbital, participate in chemical reactions. These are called valence electrons, and they are involved in the formation of chemical bonds between atoms.
Okay, so just like she mentioned in the video, when it comes to the periodic table, the number of protons in any given element is going to tell you its atomic number. So on a periodic table, there's going to be an atomic number, there'll be the symbol, and then you'll have the atomic mass. And the atomic mass is found by adding up the protons plus the neutrons. So protons and neutrons together are going to get you atomic mass. Okay, so when we talk about elements, compounds, and mixtures, so again, if you don't understand these two different terms, definitely get their definitions, and you have to understand how we can like separate them and what, just kind of what the main differences are. But for an element, it is composed of one type of atom. So if I have like, I don't know, iron, right? If I have a piece of iron and it's an element, all the atoms in there are iron. Like that's it. I'm not going to find anything else. And so because they're all the same atom, they're going to have the same properties throughout. So whatever the properties of iron are, it's going to be exactly the same, whatever piece I'm looking at of that piece of iron. And it cannot be broken down into smaller components. So the smallest component is an iron atom, right? And that's what I've got, iron atoms. There's nothing more that can be broken down. When we think of a compound, though, a compound is made up of 2 or more different elements that are put together. And when I combine elements together, I'm going to produce different properties. So like if I combine iron with a different compound, right? And I don't know, maybe make like iron oxide, right? That's going to have a different color. It's going to have different properties to it. And so it's different than just iron by itself and oxygen by itself. Okay, they're going to have completely different properties. But if I'm looking at iron oxide, it doesn't matter how much iron oxide I have, it's going to have the same properties throughout it, like or same components about it. It can be broken down into its elements, but only through chemical means. So I'd have to do like a chemical change to it, react it with something in order to get it to produce some iron or to produce like just the oxygen. So it's not, I can't just like probably do it like, I don't know, like heat it up on the pan, right? That's may not necessarily be enough of a chemical change or the chemical change that's required to break it down. A mixture is going to be made up of 2 or more elements or compounds, and it can be separated by physical means. And what I mean is I could, maybe I could sift it, maybe I could use a magnet, maybe I could evaporate, right, something out of it, or I could like boil something out of it. That's going to be how I can separate a mixture. And so the mixture is going to have the same properties as the substances that make it up. So for example, if I have like water and sand, right, and I put them together, it's still just water and sand, but now I've got like mud, right? And so if I wanted to get the sand back, I could evaporate the water, right? Use the properties of water and that its boiling point is 100 degrees. I could heat it up and at 100 degrees, all my water would evaporate, but I'd still be left with my sand. So that would be a way of separating it by physical means. I don't have to do any sort of chemical reaction to it. I'll be able to separate it some other way. And then just to explain that in terms of like pictures, right? So with elements, it's only one type of atom. With compounds, they're atoms of different elements that are chemically bonded together. And then with mixtures, right, it's going to be different types of elements or compounds that are put together. So different type of substance. Okay, and then there is a video that you could take a look at later. So then with chemistry, right, we do have those types of chemical bonds. If you don't know what these different types of chemical bonds are, I definitely suggest you, make a note of that so that you can understand them a little bit better. But a chemical formula, you do have to understand how to read a chemical formula and what everything on here means. So when we have a chemical formula, you're going to have the elements that make it up. And so again, I just put a note there that every capital letter is the start of a new element. So that's how I know that this one here is made up of 3 elements, which are sodium, phosphorus, and oxygen. And then anytime that I have a subscript, my subscript is going to tell me how many atoms I have of whatever it is after. So for example, in this case here, I have 3 sodiums. I've only got 1 phosphorus because there's no subscript here, right? And I have 4 oxygens. But when I look at this compound, so this is called sodium phosphate. But when I look at this compound, because I have a coefficient here, this is telling me that I actually have 2 compounds or 2, they're not molecules, compounds, yeah. So 2 of them of sodium phosphate. Okay, so that's how I would be able to determine what this number here means. And so this is going to be useful when it comes to balancing equations. So if you don't know how to balance equations, again, something else that you want to look up how to do. And I want to say I put a video at the very end going over balancing. So these coefficients, a lot of times when we talk about compounds and chemical formulas, we won't have coefficients, but you'll use them more specifically when you're talking about either counting atoms or when you're talking about balancing equations. Okay. I think that's in there, but I don't think we'll have enough time to watch it. Okay, so then when it comes to chemical reactions, a chemical reaction is always going to be written like this, right? When it comes in 4 through 8, you'll have your reactants on one side, you'll have your products on the other, and then you have this arrow, which is just showing you what you're yielding, right? And so I think of the arrow kind of like as an equal sign, because whenever we look at a chemical reaction, it's really showing us the law of conservation of mass. So whatever I have on the left in terms of my atoms, I have to have on the right, okay? I can't just like make something out of nothing, right? And I can't just make something disappear. Atoms will always just be rearranged to form those new products. So the chemical equations will always demonstrate that law of conservation of mass. And again, if you'll notice here, I have coefficients, right? I've got 2 oxygen molecules. And again, if I'm thinking about like the numbers of atoms, I've got 2 O2s, right? And that's what I'm showing here. This is an O2. So there's actually 2 oxygen atoms bonded together to form that molecule of oxygen. And if I were to count, right, just by looking at this formula here, I would say 2 times 2 is telling me I have 4 oxygens. And that's what I have here, right? 1, 2, 3, 4 oxygens. Over here, we've got methane. So I've got 1 carbon and 4 hydrogens. And that's what I have here. I've got my 1 carbon in the black and 1, 2, 3, 4 hydrogens on there. And so if I were to count them, like let's say if I were to look at the carbons, you know, how many carbons do I have? I have 1 carbon here. And if I look on this side, I've got 1 carbon here. So it's also following the law of conservation of mass. And that's how I would balance my chemical equations. What else? Okay, and so chemical reactions, they're going to occur in everyday life. And so, you know, just letting students know that, you know, we're going to see that out there in the real world. If you have something outside, I don't know, like an old car or whatever, right? You may have rust that forms on it. When we burn, you know, any sort of fuel in our car, right? We're burning fossil fuels. So that's going to be a chemical reaction. And all of that is producing new substances that are formed. Now, when it comes to a chemical property, right, we talked about a physical property, and that's a way to describe matter without changing the matter, right? Without changing its like whatever it's made up of. A chemical property is a way to describe how matter reacts to other matter. So if I, again, right, I'm thinking of my cup here. So I said that my cup had a certain physical property, right? Ways that I could describe it. Now, a chemical property would be a way to describe how my mug is going to react to something else. So for example, if I were to leave my mug outside, you know, in the rain and with the oxygen, would it like oxidize, right? Would it rust on me? No, right? That's not what's going to happen to it. So that's a chemical property of it. It's not going to rust. If I were to see if this could, you know, I don't know, would this dissolve in acid? I don't know. I'd have to test it out, right? And any of those things that we're talking about, if I want to see if it's flammable, if I put a match to it to see if it actually like lights on fire, right? All of those things would be a way to see if it's going to react to something else. And it might react, it might not react, but all of those are chemical properties. So it's a way to describe it and, you know, way to describe how my object here would react to something else. And again, in everyday life, right, we're going to have chemical properties that are going to be used to describe things. Okay, so we'll have one more little quiz here. So competency number 9 is going to be looking at energy and matter. So I guess a little bit of physics still in here. So with the law of conservation of energy, right, there's a law of conservation of energy, there's the law of conservation of mass. The idea between all of them is just that nothing is created, nothing is destroyed, right? Whatever we have is what we have, and all it does is changes form. So when we think of energy, energy is just going to be transferred from you know, one type of energy to another type of energy. And so the two main types of energy that you do need to know is kinetic and potential. So kinetic energy is just the energy in motion, and then potential energy is going to be stored energy. And so when it comes to energy, there's a whole bunch of different types, right? There's light energy, there's heat energy, maybe referred to as thermal energy, right? Chemical energy, chemical potential energy, kinetic, electrical, what is that other one? Mechanical, right? Mechanical energy. So there's a whole bunch of different terms and different types of energy that can be discussed. But again, the whole idea is just that it can't be created or destroyed. Now, when it comes to energy, that is going to be related to work and power. And so in science, okay, the definition for work has to do with forces and movement. Okay, so for work, that's going to occur when a force acts on an object and it causes it to move. So if I'm like pushing against the wall, right? If I have the wall and I'm pushing with all my might, you know, I could work up a sweat. I could, you know, oh my gosh, you know, I could be sore afterwards. But if I never moved the wall, I didn't do any work on the wall. Okay, so it all has to do with whether that object moves, and it has to move in the direction of the force. So just like in these examples that we have here, right? If I have this like this box, and if I'm pushing the box and the box is moving in the direction that I'm pushing it, then that is doing work, okay? But if I, in this case here, so she lifted her backpack up, right? But if she's walking in, you know, if she's walking straight, she's not doing any work on the backpack. She did the work when she lifted it up and she put it on her back. But moving forward, that's, you know, it's not in the same direction of that force that she had originally moved it. So same thing here with the moving of the groceries, right? She's picking up the bag. So she's doing work when she lifts it up, but she's not doing work on the bag when she's walking forward, because that's not how her force is being applied. So for work and power, you do have to know the formulas. You do have to know how to calculate using the formulas. So work is equal to force times distance. That's how I calculate work. And then power is just the measurement of the amount of work done over a given amount of time. So if I were to like combine these two formulas, right, I could technically say that power is equal to force times distance divided by time, right? If I wanted to calculate power and if I was given, you know, only force and distance and time or something. So you do have to understand those formulas and how they work. They do have units, which I forgot to include on here. So you may have newtons and, oh my gosh, I forgot the unit. Is it newtons for force? And
no, it's For power is walls.
What is it?
Walls. Wall, like the thing we buy in the electricity, walls. It can be kilowatts.
Oh, watts. Okay, yes.
Watts. Uh-huh.
Yes. Okay. So watts will be for the power, and then so that would be for the
work is joules.
Yeah. Joules. Thank you. Yes.
Joules for
yes.
the work.
Yes. So joules will be for work, and then force will be newtons, and then distance be type of meters, right? Meters, kilometers.
Newton meters is joules.
Yeah.
And Newton meters divided by 10 is watts.
Awesome. Okay. Thank you, Waldo. Forgot that. Have not done that in a while. Okay, so this one is going to talk a little bit about chemical bonding. So for those of you that aren't familiar with the chemical bonding, this will be helpful.
The outer shell of many atoms, hydrogen being an exception, holds 8 electrons. Atoms that have an outer shell containing 8 electrons are considered chemically stable. We often say they fulfill what is called the octet rule. When atoms combine to form compounds, they can give up, accept, or share electrons in order to assemble an octet of electrons in their outer shells. A covalent bond is formed when atoms share electrons in order to satisfy the octet rule. For example, a carbon atom holds 4 electrons in its outer shell, but it would be much more stable with 8. To gain the additional 4 electrons, carbon can share with other atoms and thereby have a completed outer shell. If 1 carbon and 4 hydrogen atoms come together and share their electrons, carbon achieves an octet of electrons. Note that each hydrogen in this compound achieves 2 electrons in its outer shell. This is the stable configuration of the first electron shell. An ionic bond forms when 2 atoms are held together by the attraction between opposite charges. The reaction between sodium and chlorine atoms is an example of how an ionic bond is formed. Since sodium has only 1 electron in its third shell, it has a tendency to give up that electron. Once it does, the remaining outer shell contains 8 electrons. This loss of an electron gives sodium a slightly positive charge. Chlorine, on the other hand, tends to gain an electron, since its outer shell already has 7. When chlorine gains an electron, it becomes slightly negative. The charged sodium and chlorine atoms are called ions. Ions of opposite charge attract each other and form ionic bonds. In this case, the attraction of sodium and chlorine form a molecule called sodium chloride, or table salt.
Okay, so if you need some more help with the chemical bonding, I know Khan Academy has some good kind of little like tutorials on how to, and I like Khan Academy because it has little videos to explain it, and then it has like practice problems that you can do to, you know, check your understanding. Okay, so competency 10, this one has to do with the law of conservation of, oops, wait a minute. Missing something here. Okay, sorry. Okay, I repeated a slide there. So it is competency 10. I think I just didn't change that information there. But with competency 10, you do have to understand the difference between temperature and heat, and really looking at heat energy. So temperature is just a measure of the kinetic energy of the molecules of a substance, right? So again, when I think of, you know, when you think of like the phase changes, like I showed you the picture of like a solid, right? And you have like the atoms like really close to each other. So when you heat something up, you cause the atoms to like vibrate more, right? And we saw it in the video. So they kind of like separate a little bit more, and that's how you get your liquid. And then if we add enough heat to them, then they're going to separate more and they'll be able to move around, and that's how you get your gases, right? So temperature is just measuring how much kinetic energy are inside of those molecules. Okay, so so that's that one. And then heat is going to be the total energy of the atoms or molecules. And so the sun is going to be that source of energy for everything on the planet. And again, once the sun hits something, right, that energy is going to be transferred into something else. And so we have, you know, all those changes that are going to be happening in real life. So with photosynthesis, that is going to be how the plants are going to capture that radiant energy and they turn it into chemical energy, which is through photosynthesis, right? They make glucose, and then that is the plant's food. So that's how they eat. Okay, and then in turn, right, I can think of, you know, I eat the plant, right? The plant gives me energy. You know, maybe I go take a jog and I get hot and I sweat, right? So I'm emitting heat. So all of that is just that transfer of energy. So in terms of heat transfer, there are going to be three main types of heat transfer. So there's conduction, convection, and radiation. And so conduction is just going to be the transfer of heat through a solid. And then convection is a transfer of heat through a fluid, and a fluid means a liquid or a gas. And then radiation is a transfer of energy through an empty space. For conduction, for example, if, you know, they say that if there's ever a fire in your house, right, before you open your door to try to leave your house, you should actually feel the door, right? So you actually put your hand on the door and you feel if it's hot. And so you're actually feeling heat transfer due to conduction, right? So you're feeling if there's heat there. Convection, you can experience this, for example, in your houses when you have the heater on, you know, when it's cold outside and you have the heater on in your house. If you've ever like raised your hand or like reached up, you know, for something high, you can literally feel that like hot air, you know, towards the ceiling, right? Compared to down lower. So if you have like a 2-story home, I have a 2-story home. So my upstairs is always the perfect temperature, right, with my thermostat, but downstairs it's always going to be colder, always going to be cooler, just because of that fluid, right, which is the gas. Hot air is always going to be, it's always going to rise. And so that is convection. And so when you turn your heater on, you can literally feel, you know, you can probably feel a cool breeze like at your feet, right? You kind of feel that warm air moving up, you know, higher up. And then radiation, you're going to have the energy through space. So like, for example, the sun is able to give us heat through radiation. So there's like no atmosphere, right, between the sun and the planet Earth, but yet we're able to receive that heat. And so there are other situations where you have, maybe if you have like a light bulb and you put your hand up close to like the light bulb, you'll be feeling that heat due to radiation. So it's not like there's a current, right? You don't feel like this fluid or like this wave of heat coming at you due to like the air, but it's just being moved through that empty space. And then there is a video here that talks a little bit more about conduction, convection, and radiation, but you can take a look at that one later. So then with electricity, you have to understand that it is just electrons that are moving, right? So we talked about the chemistry component and that an atom is made up of electrons. And so electricity is just electrons that are moving. So the electrons are going to be moving from some sort of energy source, which is always going to be some sort of like, you know, battery. Typically in you know, in most cases, you got some sort of battery that's producing the energy. Of course, there could be other things. But when you have electricity flowing, you do have to have a circuit that is closed. So in order for electricity to move, it has to make a circle, right? So a circuit, I always think a circuit circle. So if the circuit is not closed, if you don't have a circle of electricity moving, then you're not going to have electricity be able to move. So it has to be able to leave the source and come back to the source. And so when we talk about electricity, we're going to be looking at current, right? So you'll be able to measure like the current that's flowing, and conductors are going to be things that allow electricity to flow through it easily. So metals, like we mentioned, a property of metals are that they're very good conductors, and that's why most of our wires, right? Well, not most of them, all of our wires are going to be made out of metals, okay? Because they allow electricity to flow easily. And then an insulator is going to be something that stops the flow of electricity. So any of your cables in your house, right? Anything that has a wire inside of it, there's always going to be plastic around it. And so just like we talked about those properties, right? Plastics are polymers. And so polymers are not, you know, good conductors of electricity. They're going to be insulators in some cases, right? So that's going to make sure that you don't get electrocuted, you know, when you touch your cord to plug in your iPhone, right? To charge it. And so again, this is just a circuit. So the first picture is an example of a closed circuit. The other one is an example of an open circuit. Okay, and then this here would be just your switch. And then as you have electricity moving through a wire, so like I mentioned, if you have electricity moving through a wire and the wire is coiled, then that is going to create a magnet. Okay, so electricity moving through that. And that's how we get our speakers, for example. So it is electricity flowing through it. So for electricity and magnetism, when we think about those together, we do have to let students know that, you know, that magnets aren't just, you know, a magnet that you get like at school, right? But they are going to be used in everyday life. And electricity and currents are also used all around us, right? So even just like flipping the switch on your, you know, to turn your lights on is going to have to do with that electricity and currents. And then in the body, right, we have nerve impulses. So our nerves, they're actually sending signals through our body, and it is actually like through an electric current that causes them. So there is that movement of electrons. Lightning would be those ions in the atmosphere that are moving. So again, that's another form of electricity. And then, like I mentioned, magnetism is going to be something that we'll see in our speakers. Okay, now when it comes to waves, you do have to understand the properties of waves. And waves can be, you know, we can talk about light waves or we can talk about sound waves, but waves have these specific terms to them. So if you don't know the properties of waves, you know, make sure you jot that down. But you do have to understand amplitude, frequency, you know, the crest, the trough, rest position. So when we talk about a wave, frequency is going to be like how often you see, how often a wave is happening like over a certain like period of time. And then amplitude is going to be like the, like how, I guess, how big the wave is, I guess if you were to say, if you're looking from the crest to like the trough. And then I don't have it on this picture, but wavelength would be the position or the distance between the crest to crest. So I could measure this like distance here, and that would be my wavelength, or I could measure from trough to trough, and that would be my wavelength. Okay, so just understanding those main components there. And so when we talk about light energy, light is going to be moving in the form of a wave. And depending on the frequency of the wave, as well as like that, and the wavelength, it's going to give us these different types of waves that we have here. Okay, so, you know, just kind of looking at our picture that we have here, right? If we're looking at an X-ray, right, it has a certain wavelength to it. We have the visible spectrum of light. It's a small little portion on here, but you can see like what wavelength that is at. All the way to a microwave, all the way to like a radio. Okay, so you can just see how those are all related, but you know, it's something that we're gonna experience in real life. And let's see. And then when it comes to light energy, there is going to be different ways that light energy can be bent, I guess, or can be, yeah, I guess bent. So with refraction is going to be the bending of light, and it has to do with when it goes into a different medium. So for example, if you've ever been in the pool, right, in a swimming pool, and you look down at your feet may look like they're further ahead of you, right? Or they may look like they're further back from you, right? And that's just the bending of the light. So as the light enters the water, you know, like thinking about it, the air is it's not very dense, and the water is a lot more dense. So once the light hits the water, it bends because of the density. And so because of that bending, that's why we see something a little bit different. Okay, it literally looks like, you know, the object is moved somewhere else. Then reflection, that's going to happen when light bounces off of something else. And that's, you know, like when you look in a mirror, you know, the light is just, you know, bouncing off the mirror and back to your eyes, and that's how you're able to like see yourself. And so in our everyday lives, we're going to be seeing reflection, like for example, in this glass, right, like I mentioned, with water, or even just with our vision. Okay, and so our eyes, they work by, you know, bending that light, or not by bending the light, but when we wear glasses or contacts, that's actually bending the light so that we can actually see better. So I'm like super, super, super nearsighted. So I have very thick glasses, like a super high prescription. And it all has to do with where the light is being, where the picture, I guess you could say, is being projected on the back of your eyeball. And so when you have glasses, the glasses are bending it so that it's actually focusing it in the right place, okay? And so there are concave and convex lenses, and they're all gonna bend the light differently, right? So we may have like a microscope, which is, you know, got a specific type of lens so that you can see something smaller, right? So it can magnify it. And then we've also got like telescopes, right? So we're actually being able to look at things that are super far away, right? And making it easier for us to see. And it all has to do with which type of lenses that you're using, convex or concave.
How do waves behave? Badly? In this video, we're going to look at how light and sound waves behave. Before we start, you should know that waves can be transverse or longitudinal. To learn more about the properties of waves, watch this video first. Transmission, reflection, refraction, diffraction, absorption, and scattering are all typical wave behaviors. Reflection is when waves bounce off an object. Sound waves are reflected by hard, flat surfaces and is why we get echoes. You hear a delay between the original sound and the echo, because the echoed sound waves have to travel twice as far to reach your ears. Smooth surfaces like glass or polished metal reflect light in a regular way, so a reflection can be seen, like a mirror, or seeing your face in a calm pond. Transmission is when waves keep traveling in the same direction through an object, like light through a window. Absorption and reflection often go hand in hand for light waves. White light contains each wavelength, so all the colors of visible light. The color of an object depends on which wavelengths of light it absorbs and which it reflects. White objects reflect all the light that hits them and absorbs none. Black objects reflect none and instead absorb all the light that hits them. A red object absorbs all the wavelengths except the red, which is reflected. And a green object absorbs all the wavelengths except the green, which is reflected. Are the new people upstairs really noisy? If they carpet their floors, add curtains and furniture to the room, then you'll notice that they'll become much quieter. This is because some objects absorb sound waves. When sound and light waves pass across a boundary between two substances, like air and glass, they change speed. This is because the substances have different densities. The change in speed causes the waves to change direction, which is known as refraction. Because of refraction, things in water look closer than they really are. Water appears shallower than it really is. And a straw in a glass of water looks like it bends at the surface. Because the refracted light wavelengths make you think the straw is in a different place to where it actually is. When waves meet a gap in a barrier, they pass through the gap. They then spread back out after they pass through the gap. This is diffraction. The way the waves respread depends upon how big the gap is compared to the incoming wavelengths. We have diffraction to thank for loudspeakers. Sometimes waves depart from the expected path and spread out in multiple directions. This is known as scattering. We have scattering to thank for making the sky appear to be blue. The white light coming from the sun hits the molecules in our atmosphere, which causes the shorter blue wavelengths to scatter out in all directions. So waves behave in a variety of ways, depending upon what material they hit.
You're muted.
Thank you. So I said I forgot to mention that I need to add the video in there that talks about transverse and longitudinal waves. So with a longitudinal wave is going to be moving parallel to the direction of the wave, and then the transverse waves move perpendicular. So for example, when I think of light waves, like literally it's like a wave like that. But when we think of sound waves, think of like a slinky, right? So if I have a slinky and I like push the slinky, right? It's going to move the wave like in that direction. So that's the difference between those transverse and longitudinal. So light waves travel like what we think of a wave, and then your sound waves travel like a slinky, where it's just kind of like, you know, moving kind of crushed together as it goes through. And so when we think of waves, what they're gonna travel through best is gonna be through, when we think of like the different mediums of solid, liquid, or gas, they're actually going to travel best through a solid, right? Because again, if I think of the chemistry component and the particles are really close to each other. And so it's going to allow for the sound to be able to travel through it quicker, right? Because the particles are really close to each other. Whereas in a liquid, you know, they're a little bit further apart, but in a gas, they're going to be even further apart. So if you've ever been under the, you know, in the pool, you know, and you can scream underwater, you know, you can hear those things, like you can hear those little things. Or if you've ever been trying to listen to someone in the other room, you can like put a glass up to the door, right? And you can listen on the door and you can hear that sound coming to you very clearly. Okay, so let's try these practice questions here. Okay, so then we get to, so in competency 10, it's also going to be looking at, with the law of conservation of energy, we're also looking at the types of resources that may be used for that. So we'll have non-renewable resources such as natural gas, coal, and oil. And then we'll also have renewable resources, right? So such as wind and solar energy. And just understanding that, again, all of them, right? It's just the energy is just changing from one form to the other. So I'm taking wind, right? And I'm using that wind and turning it into, you know, maybe electrical energy for the house or something, right? And the same with the solar. So just kind of, again, letting students know, right, when we're talking about things, it's not just about, you know, in science, you know, we're talking about it, but we're talking about it like in the real world. And then with the sun, right, we want to remember that we have, again, it's going to be the main source of energy for the planet, but it's just that constant transfer. So when I think of, you know, your plant's doing photosynthesis, and the photosynthesis is going to make food for the plant, right? And then the plant will be eaten by an animal, and then, you know, that animal might be eaten by us, and, you know, it's just a constant changing of that energy and its form. Okay, so I'm not sure. I think we have.
Thanks for stopping by. I'm Virgil, and this is 2-Minute Classroom. If this is your first time seeing my face, welcome. If you like my mustache, you should also like this video, and I'll take it as a personal compliment. Now, on to the topic at hand, the conservation of energy, and energy in general. So, the law of conservation of energy states that in a closed system, that is, a system isolated from its surroundings, the total energy of the system is conserved. Or, more loosely stated, energy cannot be created or destroyed, only transferred or transformed. This is also known as the first law of thermodynamics. So what do I mean by cannot be created or destroyed? If a bomb explodes, it's creating energy, right? And if a ball stops rolling, its energy must have been destroyed. Well, no, because energy cannot be created or destroyed, only transferred or transformed. Let's talk a little bit more about energy. The SI unit for energy is the joule, named after James Prescott Joule, and there are different forms of energy. I'm going to talk about 5. Number 1 is kinetic energy, and is probably the energy you're most familiar with. This is the energy of motion. So any object moving through space has kinetic energy. This includes a ball thrown through the air, a swimming fish, and even a space shuttle flying through space. Number 2 is potential energy. This is the energy that an object has due to its position relative to some reference point. So a book set on a shelf has potential energy. A ball at the top of a hill has potential energy. And in both cases, they have potential energy because it can be easily converted to kinetic energy, right? If the book falls off the bookshelf or the ball rolls down the hill, we're taking that potential energy and converting it to kinetic energy. Number 3 is chemical energy. This is the energy stored in chemical bonds and released through chemical reactions. The bomb example I mentioned earlier is not energy being created, but energy being transformed from chemical energy to thermal energy. Photosynthesis takes solar energy and converts it to chemical energy. So the energy from the sun is literally being stored in chemical bonds within plants, which is pretty sweet. Number 4 is electrical energy. This is the energy due to a separation of charges and flow of electrons, also called an electrical current. All your household appliances use electrical energy and convert it to some other type of energy. For example, your blender converts electrical energy to kinetic energy to spin the blades. Your toaster converts electrical energy to thermal energy to toast your bread. And finally, number 5, thermal energy. So this is the energy given off as heat. When you start a campfire, you're breaking chemical bonds in the wood and transferring the chemical energy of those bonds into thermal energy and fire. Right? Friction is another example. So when a ball is rolling across the ground, there's friction between the ball and the ground. This friction slows the ball down, but it's actually that kinetic energy being transferred into thermal energy, which is then dissipated into the ground. It's also why you can warm up your hands by rubbing them together, because you're taking kinetic energy, the movement of your hands, and converting it to thermal energy through the friction. So those are 5 types of energy that you should be familiar with. There are others, but those are the main ones. And all those examples illustrate the law of conservation of energy, which is that energy cannot be created or destroyed, only transferred or transformed. I hope this video helped you and you enjoyed seeing my face. If you're not a subscriber already, please do so now and check out my other videos. And if you have any additional questions, please throw them in the comments. I see and read every comment you guys make, and I appreciate all your questions and love to answer them. I'll catch you next time.
Okay, so you did a good job kind of covering all of it. Well, not all of them, there's more, right? But the main types of energy. Okay, so with your competencies, you do have to also understand how the energy is created on the sun. And so energy in the sun is going to be generated by the process of nuclear fusion. And this is how all stars are going to be generating their heat. So with nuclear fusion, you have the combination of hydrogen atoms to form helium. So you have these hydrogen atoms that are being pushed together due to the high amounts of pressure and temperatures on the sun. And when they're pushed together, they actually combine to form helium. Okay, so this process produces crazy amounts of energy, and that's why we have our sun burning. Okay, so that's why we have all of that heat that's coming out to us. And so that's like that main process, but that's how all of the stars are going to be producing their energy. And of course, once if you think about it, right, you only have so many hydrogen atoms. So once we run out of hydrogen atoms, that's when the sun is gonna start to obviously not produce as much heat, right? And it'll kind of start to slowly burn out, but it has to do with how much fuel it has. There's a ton of hydrogen on there, and it's all due to the high pressure and the high temperatures. So then this one I'll go ahead and I'll let you all watch on your own. It has to do with balancing equations. Actually, no, we have time. Oh, we're doing good. Okay. So this one's balancing equations in case you don't know how to do that.
Hey, it's Professor Dave. Let's learn how to balance equations. He knows a lot about the science stuff. Professor Dave explains. When substances interact and chemistry occurs, we can describe the process using something called a chemical equation. For example, when sodium metal reacts with chlorine gas, you get sodium chloride, or table salt. The arrow here is what separates the reactants, the things that react, from the products, the things that you get. The arrow also shows the direction of the reaction. When you see a chemical reaction, it describes the substances involved, but if we want to be very accurate, we need to balance the equation so that there are the same number of atoms on both sides, because atoms won't just appear or disappear, they all have to be accounted for. For example, in order to make one molecule of sodium chloride, we need one sodium atom and one chlorine atom. But chlorine gas molecules have 2 atoms of chlorine each. So one molecule of chlorine gas will react with 2 sodium atoms to give 2 molecules of sodium chloride. We need to include coefficients before each substance to indicate how many of each we need to make the equation balanced. Let's make the distinction that these subscripts tell us how many atoms of a given element are in one molecule, whereas these coefficients tell us how many of that molecule there are. In the reaction where hydrogen gas and oxygen gas go to make water, we can see that the gases have 2 atoms each, and water has 2 hydrogen atoms and 1 oxygen atom. We will need to combine these substances in this ratio to make this equation balanced. Now there are the same number of hydrogen and oxygen atoms on both sides of the equation, even though they have rearranged their combinations. So if we have an unbalanced equation like this one that we need to balance, there's an easy way to do it. We will balance things one element at a time. If an element exists by itself, do that one last. Start with an element that is present in just one compound on each side. Let's do carbon first. On the left, there are 3 carbon atoms for every molecule of propane. And on the right, there is just 1 for every molecule of carbon dioxide. So according to the carbons, we are going to make 3 CO2s with every propane. Let's put a 3 there. Now the carbons are balanced. 3 carbon atoms on each side. Next, let's do hydrogen. There's 8 on the left and 2 on the right. That means we will make 4 waters with every propane. Now hydrogen is balanced, 8 on each side. Last is oxygen. On the right, there's 6 from CO2 and 4 from water, for a total of 10. That means we will need 5 molecules of O2 to get 10 oxygen atoms on the left side. Now the equation is balanced. There is the same number of each type of atom on both sides, showing us the correct ratio in which these molecules will have to react. These coefficients are going to be very important as we move forward, as we will have to be able to balance equations to make predictions about chemistry. Let's check comprehension.
All right, so he did provide some sample problems that you can try out, and then he goes over the answers for you. Okay, so we've got our last couple questions before we wrap up for today. All right, so the very first question had to do with the energy transformations. So we're talking about an alkaline battery inside of a flashlight. So what I would have done is I would have thought, okay, so in a battery, you know, I have my battery. First off, what type of energy is that? A battery is always going to be chemical energy, you know, or chemical potential energy, depending on how they talk about it. And then when I think about chemical, you know, chemical energy, when I turn on a flashlight, you know, what happens? Well, it's actually turning into electrical energy, right? That electrical energy is turning into light energy. It's turning into, you know, if I have it on long enough, it's also going to turn into thermal energy. So the mechanical energy has to do with energy that deals with movement or position. So a lot of times mechanical energy is talking about kinetic energy and potential energy, okay? And then again, chemical energy would be any type of stored energy, such as in a battery or such as like food, or like we said, the glucose inside of a plant, okay? That's all chemical energy. Electrical energy, you know, just think of electricity. So that was our correct answer for that one. So again, if you aren't sure, if you didn't get this one right, I would suggest, you know, looking up what each of these types of energies are. And again, I always think the best thing to do is also include a picture to help you remember what they are. For the last one, you had to balance the equation, and about half of you all got this one right. So in this question here, I just noticed it did not show, it didn't, when I recorded it, when I put it in there, it showed them as subscripts, but here it doesn't. So the numbers after the elements, they should have been subscripts, like little ones down on the bottom. For some reason, I don't know why they didn't come out like that. So the subscripts are telling you how many atoms you have of each element, right? And just like he said in the video, the easiest way to do it is just to start with one of them, right? So if you had 2 nitrogens here on the left, that would mean that I needed 2 nitrogens here on the right. I don't have 2 nitrogens because there is no subscript after it. So I would have put a coefficient of a 2 here in the front of it. And then the 2 times the imaginary 1 here would have given me 2 nitrogens. And then if I had 2 nitrogens, if I had a coefficient of 2, I would say 2 times those 2 oxygens would give me 4 oxygens. So if I go back to this side, I've only got 2 oxygens. So that's why I would have needed a coefficient of 2 here as well. Okay. And so that was looking for, this question was just asking for NO2, but you always want to balance the entire equation before you actually come up with an answer. Okay. Just to make sure nothing changes. All right, so that is about it for our review session. So I thank you for coming. I hope this was useful. And please let me know if you have any questions.